So let's get started. Yeah. So thank you for coming. Today's speaker is Wataru Yuasa in Kyoto University, Japan. He will talk about state-clasp correspondence for skein algebras. Please.
Hey, thank you for introduction and thanks for inviting me this GAP seminar. So today I would like to talk about state-clasp correspondence for skein algebras. So this correspondence gives isomorphism between two non-commutative algebra called skein algebra. One is stated skein algebra and another is clasped skein algebra. So this skein algebra is related to the quantum cluster algebra. So associated with some surface and some gauge group G. So we firstly introduce I explain my purpose of this study. So first, we introduce this unpunctured surface. So let sigma be an unpunctured surface with special points M and boundary intervals B. So unpunctured surface means an oriented compact surface with boundary. So we assume that this sigma is triangulable and every boundary component has a marked points, special points like this. We do not consider punctures. The punctures is interior marked points. So a boundary interval is a connected component between the marked points like this. So, okay, so let's explain relation between this cluster algebra and these skein algebras. So for such surface and some gauge group, we can consider the modular space AG sigma of decorated twisted G-local systems. So this geometry has, we can consider algebraic side of this geometry. So which is related to cluster algebra. We denote it by AG sigma. And this cluster algebra is associated with decorated triangulation, shield pattern of decorated triangulation, and which is generated by A variables. And we also, this cluster algebra expect to coincide with the function ring of this modulus, function ring of the open subspace substack of this modular space AG sigma. And this function ring is generated by matrix questions of Wilson line. The Wilson line is some monodromy between the boundary components like this. So by such decoration, we can define the monodromy between the boundary intervals. And this matrix questions generate the function ring. Due to the result of Ishibashi and Oya and Shen, And these algebra, they show that this algebra is isomorphic. So today we consider the quantum version of this correspondence in from the viewpoint of knot theory. Okay. So we considered two skein algebra. Skein algebra is space of quantum invariants on the surface. So there are many versions of skein algebra. The first is clasped skein algebra, so which is corresponding to the cluster algebra, AG sigma. And another is stated skein algebra. So we denote it by SG sigma B, and clasped is denoted by SG sigma M. So then we give an isomorphism between the boundary localized clasped skein algebra and reduced stated skein algebra. So reduced stated skein algebra is denoted by using this bar. So this localization is needed because boundary interval is corresponding to the frozen variables in the cluster algebra. So we need to localize at boundary interval. So we will explain this isomorphism called State-clasp correspondence. So this isomorphism is given by explicitly by using diagrams. So let us explain this correspondence. Okay. So skein algebra is an element of skein algebra is described by using g-waves. So g-waves is a unitary valent graph in sigma cross interval. So which has admissible coloring. So each edge has colored by the fundamental representation of G. So this color is corresponding fundamental representation of G. The admissible condition means the dimension of invariant part is 1. And we have to define the skein relation for each G. We explain this skein relation later for rank 2B algebra. Okay, so we defined two skein algebra. M is clasped skein algebra, and B is stated skein algebra. So G-waves in clasped skein algebra is like this. So every endpoint is touched to the special points like this. And endpoints at the special points have elevation, so which is described like this. The most highest, this strand has most highest elevation, so which is corresponding to the diagrams in sigma cross interval. So this one. And the second one is here. So the second one is here. And the third one is here, this one, this strand. So we denote such waves on the surface like this. Okay. And next, we introduce stated G-waves in stated skein algebra. So stated skein G-waves in stated skein algebra is ended to the boundary interval here. And every endpoint has state. So in this case, epsilon1 is epsilon2, and that is states of this G-wave. So in sigma cross interval, these G-waves is can be seen as like this. So every endpoint has height. So in this case, this omega k has most highest one. And this omega I is second, and omega j is the lowest one. And we describe these waves in on the surface like this. The highest one is the most in this case, the most highest one is ended to the most upper side like this, and the second one is here, and the third one is here. So by using such description, we denote the G-waves in sigma cross interval for stated skein algebra. And the state is state. So if S is state for some state for some H is colored by omega. So then state is a number. So 1, 2, dimension of fundamental representation colored by omega. So this is state. So we consider such G-waves for stated skein algebra. Okay, so first, we explain clasped skein algebra and the relationship between relation to the quantum cluster algebra. So in this section, we assume the number of marked points is greater than or equal to. We need this assumption. So for SL2 case, so Muller shows that the boundary localized clasped skein algebra is equal to the quantum cluster algebra associated with SL2 and sigma. And he showed that he showed this equation by using A equal U. U is sorry. U is upper cluster algebra, quantum upper cluster algebra. So firstly, he shows such inclusion. So A is included to the skein, and it is included in upper cluster algebra. And next, they show this equation. So we get A equal S equal U. So then we get this equation. And we should firstly introduce SL2F. So SL2F is tangled in sigma with Kaufman bracket skein relation. And so this clasped skein relation, this relation is compatible to this quantum cluster algebra. For each triangulation is corresponding to the cluster of this cluster algebra. And for each triangulation, we consider this such quiver, and we can construct quantum cluster algebra. And each vertices of quiver is corresponding to A variables. And in this case, this A variable is corresponding to the SL2F, or is represented by such ideal arc. And 2 is corresponding to this one, and 3 is this one. So by this correspondence, they construct cluster algebra in skein algebra. Okay. And next, we explain the SL3 case. So SL3 case, SL3 wave is represented by oriented arc. So because the fundamental representation is pi 1 and v pi 2, and v pi 1 is isomorphic to its dual. Sorry, not isomorphic. So we need this one and this one. Okay. Yes. And okay. In this case, Ishibashi and myself showed that clasped boundary localized clasped skein algebra is included into the SL3 quantum cluster algebra. So the SL3 wave has such skein relation. And we use Frohman-Shikola's clasped skein relation like this. And the correspondence, example of correspondence between cluster and skein algebra is the following. So for cluster corresponding to the decorated triangulation, this sigma, this triangulation, which is corresponding to such quivers. And each vertices of quiver is a variables. So in this case, it has a face variable. So this variable is corresponding to this trivalent vertices. And 2 and 3 is corresponding to oriented edges. And as a decorated triangulation, so this is delta minus, has such quiver. And in a similar way, so this face variable is corresponding to this trivalent vertex, trivalent graph. So this tripod has source vertex, and the +1 is sink vertex. And this is the difference between plus and minus. And the next, we also showed such inclusion for SP4. So SP4 skein relation is given by Cooper bar, like this. So many skein relation. And we also defined clasped SP4 skein relation, like this. So in this case, so V equal Q. So by using such skein relation, we defined clasped skein algebra and construct inclusion from skein algebra to the quantum cluster algebra associated with sigma and SP4. So we show an example of waves corresponding to the cluster variables. In SP4 case, cluster is constructed from ideal triangulation with signs and assign of such corner. And this decorated triangulation is corresponding to such quivers. So there are 2 face variables and 2 types of variable vertices. So weight 1 and weight 2. And in this case, this vertex is corresponding to these waves. And this weight 2 vertices is corresponding to these waves. And 3 is weight 1 is this one, and weight 2 is this arc. Sorry, so this so doubled edge is corresponding to irreducible representation 5 is 5-dimensional. And this single edge is corresponding to 4-dimensional irreducible representation. And the other one is -1. So this quiver is this one. And the weight 1 face vertices is corresponding to these waves, and weight 2-1 is corresponding to this one. And so in the difference between SL2 case and SL2 case and SL3 and SP4 case is in SL3 and SP4, there are many clusters not associated with ideal triangulation. So in SL2 case, every cluster is corresponding to the ideal triangulation. However, there are many clusters we cannot construct from the ideal triangulation. So by such reason, we cannot construct the skein, the cluster, quantum cluster algebra in skein. However, we can give a special generators of clasped skein algebra, so which is corresponding to simple Wilson line. So by using this generator, we can construct inclusion from skein to the quantum cluster algebra. So our method is different from the Miller's method. And in SP4 case, SP4 skein algebra is generated by over, so this is SP4 skein. Generated is algebra over ZQ 1 over quantum integer 2. So however, the quantum cluster algebra of SP4 is over ZQ. So we have to adjust this difference. So to construct this inclusion, so we define ZQ subalgebra of the clasped skein algebra of SP4 by using crossroad wave. So crossroad wave is waves with only with 4 valent vertices. 4 valent vertices represent such linear sum of this SP4 waves. So by using this crossroad, we can construct linear basis of SP4 skein algebra. And by considering which is called, this basis is called basis wave. So by considering ZQ span of base wave of SP4 sigma. So this module is closed under multiplication. So we can define ZQ subalgebra. So this ZQ subalgebra is corresponding to this cluster algebra. Okay, so we suggest some problems about this clasped skein algebra. So first, SL2 case, clasped boundary localized clasped skein algebra is equal to the quantized quantum cluster algebra. So in SL3 and SP4 case, we only have inclusion. So the problem is this equation. In classical case, the combining Ishibashi and Oya and Shen's result and our result. So we can show this equation in the classical case. So first, we get this inclusion in the quantum case. So, and Ishibashi and Oya and Shen shows A equal U, and U equal the function ring of the moduli space. Yeah. And using, so this function ring is generated by matrix coefficients of Wilson lines. By using this generator, we can construct maps from function ring to the reduced stated skein algebra. And by using state-clasp correspondence, we get a map from here to the clasped skein algebra. So by using such maps, we get inverse of this inclusion. So we get this equation. So for the classical case. In the quantum case, we do not have such geometry and such generators. So we cannot show, we cannot construct such map from upper cluster to the skein. So this is the reason why we cannot obtain this equation in the quantum case. Okay, so next problem is give a positive basis of the quantum cluster algebra via skein theory. So recent result of Mandel and King. So SL2 case, skein algebra has bracelet basis. It is known that this, so it, sorry, so I don't know. So it becomes basis of clasped skein algebra. And on the other hand, clusters in the cluster algebra, so quantum database is obtained by GHKK. And this quantum database has positivity. And Mandel and King shows the coincidence of bracelet base and the quantum database. So by using this correspondence, we know that the bracelet basis is positive basis. However, we do not know how to show bracelet basis is positive only using the skein theory. And so this is SL2 case. So the question is that, what is the bracelet basis for other G, especially SL3 and SP4 case? SL2 case, bracelet basis is corresponding to Chebyshev polynomial of the first kind. And the candidate of the bracelet basis for other G is constructed from orthogonal polynomial of simply group G. So I expect it. So such orthogonal polynomial is defined by this paper, in this paper. So this is called C function. C function is cosine function for such G. And this is corresponding to the Chebyshev polynomial of the first kind. And they also define S function. This is sine function. This sine function is a higher version of Chebyshev polynomial of the second kind. So I expected that we can construct, we can give a definition of bracelet base by using such orthogonal polynomial. Okay. However, I don't know. So it is good strategy or not. Okay. Okay, so related to this positivity, we show some Laurent positivity, quantum Laurent positivity in the special case, for special case. For elevation preserving waves, so we define such waves, such types of waves. So which is constructed by using ideal triangulation. So this wave is when we expand these waves in the upper cluster algebra. So then the coefficient has coefficients become positive. So we show such positivity. Elevation preserving wave is constructed by attaching such fundamental pieces. So fundamental pieces is such forms. And we can connect these pieces, preserving elevation of each piece. So this is the highest one, and this one is the highest one in this triangulation. So we connect this highest one. By using such construction, we get elevation preserving wave. And all such waves has quantum Laurent positivity for the cluster associated with decorated triangulation. Okay, next. And the third problem is characterize G waves corresponding to cluster variables. SL2 case, it is very easy because every cluster is corresponding to the ideal triangulation, and the cluster variables is corresponding to ideal arcs. So this problem is solved in the case of SL2. And however, SL3 and SP4 case, we do not know every cluster because there are many clusters other than associated with ideal decorated triangulation. So we conjecture that elementary web. Elementary web is indecomposable basis web. And such web minus invariant part of Donaldson-Thomas transformation. And this set is equal to the three type webs we introduce such webs. And it is also corresponding, this webs is corresponding to the cluster variables. So this is just a conjecture. So Donaldson-Thomas invariant part of Donaldson-Thomas transformation has such webs in SL3 case. So this web is invariant under Donaldson-Thomas transformation. And the SP4 case, there is this web is contained in this invariant part. So so our evidence of this conjecture is infinitely many examples of cluster variables. So we construct, we get many webs which is corresponding to cluster variables by using mutations and by calculation by hand. So for example, so flip has realized by 1, 2, 3, 4, 5, 6, 7, 8 mutations. And this mutation sequence is realized by such webs. So these webs is three types we call. So because, so for example, so this web is described by an immersion of this graph. So this is tree type. So all webs appearing in this cluster is tree type. And another example of cluster is adjacent cluster to the decorated ideal triangulation. So we get such clusters. So in this case, these webs is, all these webs are tree type. And there are more examples, so like this. So very complicated web. However, this one is also tree type. So this is described as immersion of such trees. Okay. So by clasping these univariant vertices, we get this web. And we also construct an infinite sequence of cluster variables by using webs. So this infinite sequence is corresponding to the mutation obtained by clusters mutation at this Kronecker subquiver. So these webs is example of cluster variables. Okay. So this is topics related to the clasped skein algebra. Okay. We next explain the stated skein algebra. Okay. So first, stated skein is introduced by Bonahon 1. So they use state, so web with state to construct quantum trace map. So in this case, state is plus and minus, and in our notation, this is 1 and 2. 2 is plus maybe, 1 is minus. And after that, Tanley defines the stated skein algebra. So we denote it by SB. And so we define let us define the stated skein algebra for SL2. Stated skein algebra for SL2 is spanned by tangles with state. This lambda is a set of 1 and 2. So because it is 1 and dimension of irreducible representation of SL2. And the skein relation is given by such relation. So this relation is corresponding to sticking toric. So sticking toric is used by constructing inclusion from clasped skein algebra to quantum cluster algebra. So this relation is corresponding to the sticking torics in the clasped skein algebra. So by Constantine and Ray, they define Butt-arc ideal. So this ideal is submodule generated by Butt-arcs. Butt-arcs is such arcs. So very small returning arcs from left side of the marked point, special point, and to the right hand side of the special point. And the state is increasing from left to right. So this is Butt-arcs. They show that this submodule is left and right ideal. So the proof is the following. So multiplication of this Butt-arcs and any waves is described by such waves. So in this form, we do not know this waves is contained in Butt-arcs because there is no Butt-arcs. However, using sticking toric here, so we get then by sticking toric, So we get such expansion. So there is some waves and one, I, and two, and with some questions. By using sticking trick, this wave is expanded like this. And this strand is through these arcs and get such small returning arc. And using skein relation, this sum is becomes such waves. So this wave has buttocks, so it contains in the submodule of buttocks. So we can show in this way, we can show this buttock submodule is buttock ideal. So by quotient of the stated skein algebra by buttock ideal is called reduced stated skein algebra. So we denote it by S bar with of B. And they and U shows that reduced stated skein algebra is isomorphic to the clasped skein algebra with localized boundary. So our aim is to define the reduced stated skein algebra for higher case and give an explicit isomorphism between this reduced stated skein algebra and clasped skein algebra. So we call this isomorphism state-clasp correspondence. So now we get some result about on the SL3 and SP4 and G2 case. Okay, so let us define the reduced stated skein algebra. So SL3 case stated skein algebra is given by Higgins. So the relation at the boundary interval is following. One. So by using this relation, we get a stated skein algebra. And in this case, by using this relation, we can show sticking trick like this. And we shows buttock submodule. In this case, buttocks is defined similarly. So left state is smaller than the right state. And this wave is surrounding special points. So this submodule generated by this buttocks is left and right ideal generated by buttocks. So the proof is similar to SL2 case. So first, we consider the product of any waves and buttocks. And then we get such waves. And using sticking trick here, So we get the linear combination of such waves. However, by using stated skein relation, we describe this linear combination only the linear combination with buttocks. So this waves is contained by submodule generated by buttocks. So we can show buttock submodule is left and right ideal. So by this lemma, we can define the reduced version of stated skein algebra for SL3. And the SP4 case, skein relation is this one. So this skein, stated skein relation is defined in our paper. So state is corresponding to the dimension of illusory representation. So the single edge has state 1, 2, 3, 4, and doubled edge has state 1, 2, 3, 4, 5. So by using this skein relation, we can define the stated skein algebra for SP4. And in this case, we can show the sticking trick. So this one. And by similar way, we can show but submodule generated by buttocks is left and right ideal. So we can define the reduced version of stated skein algebra for SP4. So this is a preparation for the State-clasp correspondence. So next, we explain the State-clasp correspondence. State-clasp correspondence is isomorphism between the stated skein algebra, reduced version of stated skein algebra and boundary localized clasped skein algebra. So we construct isomorphisms and its inverse explicitly. So first, we explain SL2 case. Clasped skein has G wave, so which is ended to the special points, and each edge has elevation. So this is first floor and second and third and fourth. So then we send such end like this. So the highest edge is sent to the rightmost one. And the second is, this is second one and this is third one. Sorry. One is the lowest one. Sorry. So this is second, third. Okay. So this edge has this edge is second one, and so this one is sent to this end. And the third one is sent to this one. And the lowest one is leftmost one. And we assign highest state to every endpoint. So this is map from clasped skein to the stated skein. The inverse map is following. So for edge width state 1 is sent to this webs. So this blue edge is inverse of boundary interval. Inverse of this arcs. And the second one is sent to this webs in clasped skein algebra. So we can see these two maps is inverse each other. And the SL3 case, clasp to the state is constructed similar way. In SL3 case, highest states is 3. So we assign 3 for each endpoint. And stated arc is sent to this webs in clasped skein algebra, like this. And the SP4 case is similar, or from clasped to the stated. In this case, highest state for single edge is 4, and double edge is 5. So we assign this state for these webs. And the inverse map is constructed as following. So first is sent to this one, and second is sent to this one, the third is this one, the fourth, this one. And double edge is sent to such webs. Okay. So by definition, we can easy to see that. So this composition is identity. So because, for example, SP4 case, okay. First, we send clasped webs to the stated one like this. And the highest one is sent to the, by sliding to the left special points. So these webs is returned to this marked special points. So we get such identity. The other one is little complicated. However, so then we use sticking trick. For example, SP4 case, state 1 arc is sent to such webs in clasped skein algebra. And this one is represented by such webs. And sending these webs to the stated skein, so then we get such webs. So at a glance, so this stated web is different to this one. However, so adding webs with buttocks, so this is vertex. So we can consider such linear combination. So in reduced stated skein algebra, and using sticking trick here, so we get this web. So sticking trick is stick such arcs to this boundary interval like this. So we get this simple arc. So we can show this arcs with state 1 is returned to arcs with state 1. So in a similar way, so second and third and fourth state is also can be returned to themselves. Okay. And so we also explain some properties for SP4 skein algebra. So in SP4 skein algebra, so in a similar to the SL2 case and SL3 case shown by Ray and Higgins. So such lemma is such equation holds. So this cutting property of stated skein is used to construct injective algebra homomorphism from stated skein algebra of sigma to stated skein algebra sigma prime. Sigma prime is so obtained by sigma to sigma prime obtained by cutting here. Okay. So we also show that there is such an injective algebra homomorphism for SP4. As a corollary, so we can show the clasped skein algebra is an ORE domain as follows. Firstly, we consider localized clasped skein algebra by using state-clasp correspondence. This clasped skein algebra is isomorphic to stated skein algebra. And by using cutting homomorphism for triangulation, we get inclusion from this stated skein algebra to the reduced stated skein algebra of triangles, disjoint triangles. For each component, this reduced stated algebra is isomorphic to the clasped stated skein algebra of disjoint triangles by state-clasp correspondence. And for each component is triangle. So then we showed that in the triangle case, S equals A. So we get isomorphism between this skein to this cluster algebra. So, and this cluster algebra has inclusion to the quantum torus by toric frame. So consequently, we get an inclusion from the clasped skein algebra to the quantum torus. So we can show this algebra is all domain. So this is one of the application of the cutting homomorphism. So finally, we chose some works in progress. So we also we are also constructing the state-clasp correspondence for exceptionally algebra G2. So rank 2 the algebra. So G2 case, Cooper-Bag gives skein relation. However, so it has some errors. So Sakamoto and Yonezawa correct these errors, and we use their skein relation here for internal webs. And clasped skein relation is given by such relation. So we define it. And stated skein relation is, I think stated skein relation is also given by using state-clasp correspondence. But however, so I do not have complete list of stated skein relation. So I have to list such relation. So anyway, so we expect that this gives a state-clasp correspondence for G2. So G2 has two fundamental representation. So one is 7-dimensional irreducible representation, which is represented by single arc. And the other one is 14-dimensional irreducible representation. So there is state from 1 to 14. And we send this stated arc to the clasped skein algebra. So this map is given as following, and like this. So this is our construction of state-clasp correspondence. So the inverse map is similar, constructed in a similar way. Slide the arcs at special point to the right-hand side and assign highest state to each end. So these maps give state-clasp correspondence. So, and we also works in SLN case. SLN case, the stated skein algebra is already introduced in the paper of Ray and Shikola. They use Shikola's N-web. So N-web is N-variant vertices with oriented edges, N-oriented edges. However, so these web edges is colored by only the vector representation. So this web doesn't consider the coloring of fundamental representation. So they only consider vector representation. However, it is sufficient to define the stated skein algebra. So however, we by constructing state-clasp correspondence, it is useful rather than Tsukasa N-web MOI graph. We use MOI graphs. MOI graphs has a trivalent graph with such coloring, so which is corresponding to fundamental representation of SLN. And by using this MOI graph, we are going to construct the state-clasp correspondence. So this is our future work. Okay, so a little early. So this is all. Thank you very much.
Thank you for the nice talk. Let me first stop the recording.